Video, I'd like to talk about reaction mechanisms as covered in chapter 12.5. A reaction mechanism is a series of individual reactions called elementary steps by which the overall reaction takes place. It is a list of specific chemical reactions that occur on going from reactant to product, and the elementary steps add up to the overall reaction. Think of the mechanism as the pathway by which the reactants become the products. Our goal is to use kinetic information, namely the differential rate law, to deduce the reaction mechanism. One big question is why? Why would we want to know the exact series of steps the reactants go through to become the products? Well, one is just curiosity. I remember when I was first studying chemistry, I thought that the holy grail of chemistry would be to actually visualize a chemical reaction take place. Watch bonds being broken and bonds being formed and know the order in which that occurs. That would sort of like be almost magical. But a practical reason why we want to know the mechanism is to understand the reaction better. If I know the mechanism by which, say, an industrially important or useful reaction takes place, then maybe I can tweak the conditions to improve the yield or efficiency of the reaction. Okay? Now, one important thing to understand is that a mechanism is really a proposal or a hypothesis, and we can never absolutely 100% prove that a mechanism is correct. We can simply say the proposed mechanism is consistent with all the experimental data. Well, of course, you're not going to publish your mechanistic proposal until you've done every single possible experiment you can imagine, but it's always possible that you can propose a mechanism that you believe is correct because it's consistent with the experimental data, but next week somebody publishes the result of an experiment that shows that your mechanism is incorrect. That's just how science works. So let's begin with the concept of an elementary step. As I said, an elementary step is an individual chemical reaction that tells exactly what's taking place in a step in the mechanism. Now, we said earlier in the unit that you cannot write the rate law for the overall reaction simply by looking at the stoichiometry. It doesn't work that way. But in an elementary step, because it is fundamentally telling you what is colliding with what, you can write the rate law for the elementary step directly from the equation for the elementary step. We can also describe it in terms of the molecularity, which is the number of particles that collide in that step. So for example, if my elementary step is one molecule of A reacts to become something, we say that it's a unimolecular step because there's only one molecule on the reactant side, and the rate law for that step would simply be first order with respect to the concentration of A. On the other hand, if two molecules of A collided in the elementary step to form the product, we would say that's a bimolecular step, and the rate law would be second order with respect to A. Why? Because two molecules of A are colliding in that step. If one molecule of A and one molecule of B collided in that elementary step, it would still be a bimolecular reaction, but now the rate would be first order in A, first order in B, second order overall. An elementary step in which two molecules of A collided with one molecule of B to form products would be called a termolecular step. The rate law would be second order with respect to A, first order with respect to B, third order overall. And finally, an elementary step in which one molecule of A collided with one molecule of B while simultaneously colliding with one molecule of C to form the products would also be a termolecular step, and the rate would be first order each in A, B, and C for an overall third order rate law. As you may guess, termolecular steps are extremely rare. So let's do a couple of these. We'll write the rate law for the following elementary step and state the molecularity. In the first reaction, CH3NC is simply rearranging to form a different molecule. So we would say the rate is equal to a rate constant times the concentration of CH3NC, and that would be a unimolecular step. In the second reaction, one molecule of ozone collides with one molecule of NO, so we would say that the rate is equal to rate constant times the concentration of ozone times the concentration of nitrogen monoxide, and that would be a bimolecular elementary step. In the third reaction, one molecule of ozone splits apart to form one molecule of O2 and one atom of oxygen. The rate would simply be first order in ozone, and that would be a unimolecular step. And finally, in the fourth example, one molecule of ozone collides with one atom of oxygen to form two molecules of O2. The rate would be first order each in ozone and oxygen, and that would be a bimolecular elementary step. So, what needs to be true in order for a proposed mechanism to be, quote, consistent with experimental data? Well, a proposed mechanism must meet two criteria in order to be consistent. First of all, obviously, the elementary steps have to add up to the overall balanced equation. That would be a pretty weak proposal if the stoichiometry didn't even work out, so that's pretty obvious. The second, the proposed mechanism must agree with the experimentally determined rate law for the overall reaction. What does that mean? The proposed mechanism must not only list all of the elementary steps that add up to the overall reaction, but it also must state which of the elementary steps in the mechanism is the rate determining step. The rate determining step is the slowest elementary step in the mechanism. It's sometimes called the rate limiting step as well. It controls the overall rate of the reaction. Obviously, the overall reaction cannot go any faster than the slowest step in the mechanism. Now, the rate law that you write for the rate determining elementary step must be the same as the experimentally determined rate law for the overall reaction. Okay, so if these two criteria are met, then you can say your proposed mechanism is consistent with the experimental data. So here's an example. Nitrogen dioxide reacts with carbon monoxide to form nitrogen monoxide and carbon dioxide. In the laboratory, using all the techniques we've learned so far in this unit, we've discovered that the experimentally determined rate law for this reaction is that the rate, defined as the decrease in concentration of NO2 with respect to time, is second order with respect to NO2. So, here is our proposed mechanism. We propose that in the slow or rate determining first step, two molecules of NO2 collide to form one molecule of NO3 and one molecule of NO. In the second step, that molecule of NO3 reacts with molecule of carbon monoxide to form one molecule of NO2 and one molecule of CO2. I should point out that NO3 is referred to as an intermediate. And an intermediate in a reaction is a substance that is produced in an early step, consumed in a later step, and does not appear in the overall balanced equation. So, what would be the rate law for each elementary step? Well, for the first step, the rate is equal to a rate constant times the concentration of nitrogen dioxide squared to the second power. For the second step, the rate would be equal to another rate constant times the concentration of NO3 times the concentration of CO. Again, remember, the individual steps in a mechanism are elementary steps, and you can write the rate law for an elementary step directly from the stoichiometry. Does the rate law for the rate determining step match the rate law for the overall reaction? And we simply look and we see that the answer to that question is yes, it does. Okay? Both the rate law for the proposed rate determining step and the experimentally determined rate law for the overall reaction are second order in the concentration of NO2. Do the elementary steps add up to the overall reaction? Well, let's take a look and see. I form one molecule of NO3 in the first step, which gets used up in the second step. And I form one molecule of NO2 in the second step, which cancels one of the two molecules of NO2 in the first step. And that gives me an overall stoichiometry of NO2 plus CO reacts to form NO gas plus CO2 gas. So the answer is yes. The elementary steps add up to the overall reaction. So is this proposed mechanism consistent with experimental data? Yes, it does. It meets both of our criteria. But does that mean we've proven the mechanism to be correct? No. All we can say is that our proposed mechanism is consistent with the experimental data. Let's do one more example. For the overall reaction, 2 molecules of NO2 react with 1 molecule of F2 to form 2 molecules of NO2F. The experimentally determined rate law shows that the overall reaction is first order in NO2, first order in F2, second order overall. Is the following proposed mechanism consistent with the experimental data? Pause the video, look at that for a minute, and you think about whether it is consistent or not. Well, the first criterion must be that the elementary steps add up to the overall reaction. In this case, we have, in the first step, which is proposed to be the rate determining step, NO2 reacts with F2 to form NO2F plus F. Again, the F atom that's formed is an intermediate. In the second step, which is fast, the F atom reacts with NO2 to form NO2F. So I cancel the intermediate that's produced in the first step used in the second, and I get 2 NO2 gas plus F2 gas forms 2 NO2F gas. Okay? So our first criterion is met. Yes, the steps add up to the overall observed stoichiometry. The second criterion is the rate law for the proposed rate determining step the same as the experimentally determined rate law? Well, for the proposed rate determining step, the rate would be first order in NO2, first order in F2, which matches the experimentally determined rate law for the overall reaction. So I would say that since both criteria are met, yes, this mechanistic proposal is consistent with the experimental data.